give these back to the end. These are your project descriptions. Everything looks good. So you're on track. Don't forget you have your update to give us on, I guess it's Friday. Only two general comments I would say is that some of you I noticed, the TAs wrote some comments on here. And two most common comments, which I agree with, is that sometimes the scope seems pretty big, so don't feel, like you have to cover every paper to feel. If you want to focus down a little bit, that's good. And keep in mind, you're supposed to be summarizing especially the theoretical results in that particular area. So that's probably the most common comments. But otherwise, I think you look pretty good. Please look really good. So we'll give them back to the end of class. Homework's due Friday, and today we are doing undirected graphical models. There's many different types of graphical models. So there's undirected, there's directed, and then there's the two most common ones are directed and undirected. You did directed graphical models in 701. Yes. You might have called them Bayes nets, which is a very bad name, but that's what they're called. But we're going to focus on undirected graphical models. I believe you did less of that. Too much undirected graphical models? Yeah. Sounds a lot. Because then we go fast. So I think I'll tell you some things you didn't do. So, what are graphical models? Well, they're really just a way, I think of them almost as an exploratory tool for summarizing multivariate data. And they're very common now. You see them like with genes, for example. And I'm going to use the terminology which seems to have fallen by the wayside, but in the olden days we used to distinguish networks and graphs. A graph meant every node was about a feature, like gene 1, gene 2, gene 3, gene 4. Whereas a network, every node was a person, an observation. But these days it seems to have gotten much blurrier, but we're definitely talking about graphs. So we're talking not about each node being a person, not like a social network. We're talking about, I've measured 100 genes on every person, and we're trying to understand the relationship between the genes and features. And so I uploaded 2 chapters. There's quite a long chapter on undirected graphical models, and then a chapter about non-parametric graphical models. So we're going to start with the parametric case first. In fact, it occurred to me that before we even start with the usual undirected graphical models, I thought I'd start with something simpler, which is just a correlation graph, which is very popular actually in bioinformatics. It's a very simple thing, but it's actually quite a useful thing. So let's imagine then that we have data, and maybe I'll do this actually, because it can get confusing whether you're talking about features or observations. I've never found a notation that I quite like. But what this means is these are n observations from P, but each one of these is a vector. So a typical one looks like this. I'll write it like this. So there's D. So one vector looks like this. It's got D features. These are the D genes I've measured on n people. I don't know if I like that notation, but it's hard to come up with a good notation because I just don't want to confuse the ith person and the ith gene. The graph, whatever graph we're going to draw, is going to have G nodes. It's about the genes again. And before we get to the undirected graphs there, or the ones that we did in 701, let's just do the correlation graph, which is a simpler one, where, so we're going to have a node for each variable. So, by the way, if I represented the data matrix, it would be n by d. So each row would be a person, and each column would be a gene. And we're talking about now the columns. And I'm taking the correlation between any pair of columns will be a correlation graph. So here's x1, here's x2. So I've already screwed up because I guess if I want to stick to my notation, I should do this. And so on. And a correlation graph is very simple. You just connect things that are correlated. And there's many different ways to do it. You could connect things that are highly correlated. You could connect things that are significantly correlated. That's probably the most common one. So we might draw something like this. This is not the undirected graph about independence relations. This is simply correlation. So what we're doing is we're putting an edge between two nodes, between, let's say, I and j. If, for example, we would reject the null hypothesis, and I'll write theta ij, if we reject, where theta ij is just the usual Pearson correlation. So in other words, you just take every pair of genes, you compute the correlation, you do a test whether it's 0 or not, and if you reject, you connect it. That would be a common way to construct a correlation graph. They're very simple, they're very easy to construct, they require very few assumptions. One question is, how would I do this? So if I want to test, so theta ij, let's write down what the correlation is. It's the expected values xi minus its mean and xj minus its mean over corresponding standard deviations, right? That's just the usual correlation coefficient between 0 and 1. Suppose I wanted to test versus the alternative. How would I do that?
Wouldn't you also have to do a Von-Browning correction due to the fact that
So you're one step ahead of me. Let's focus, good question, but let's just focus on a single edge right now. How do I test this hypothesis? So okay, you see the Fisher transform. Good. You could, there's many different ways you can do it, but a very good way is the Fisher transform, where you take what you do is you take the sample correlation, so that's just the sample version, and you do this transformation. And the reason, how many of you have seen the Fisher transform? Oh, not very many, okay. So the reason why you do this is because Fisher showed this has a very simple distribution. It's approximately normal with mean 0, under the null hypothesis, it's approximately normal with mean 0, variance 1 over n minus 3. So then, now that makes a very easy test, but we would reject if Zij is bigger than the normal quantile over. And the reason for doing this transform is Fisher showed that that's a good approximation to the distribution. Actually, there's a way to do an exact test that is without an approximation. Does anybody know what that is? Suppose I wanted to make sure that my p-value really is less than 0.05, 5% of the time, without doing any asymptotic approximations. I'm going to do this test and compute p-value. Here I'm getting an approximate test. Do you know the exact test? Did you do permutation testing? It's a very cool thing. You just take, all you would do is you take the two columns of data we're interested in. Right? So we're looking at column I and J now. You compute the correlation. Now you permute. Do all possible permutations and recompute the correlation. And say how often is the computed correlation bigger than or equal to the one that I just computed from your unpermuted data. That gives you what's called a permutation p-value. That's exact. That doesn't require asymptotic loss. But this is usually pretty accurate anyway, so I just wanted to mention that as an aside. However, someone raised a question here, which is about simultaneous testing, is if I do this test, the probability of a false rejection is by definition alpha, right? That's what a level alpha test does. We did that 7 to 5. but I'm actually doing about order d squared tests. So how do I take care of the simultaneity? There's two ways to do it. So to correct for multiple testing, that is, if I test, even if there was if everything was totally uncorrelated, if I test enough of them, I'm going to start finding false positives because it's like flipping a coin many times. So we need to do some sort of correction. The two easiest corrections are the Bonferroni correction, where you test, you don't test at level alpha, you replace that by alpha divided by the number of tests, which I guess would be d choose 2. So every test is done at level alpha over d choose 2, and then the probability of at least one error is no more than alpha. You're going to lose power, right? It's going to be harder to reject in a very large graph. There are other ways to correct. For example, you can use a bootstrap method, which we'll talk about when we get to the bootstrap. There's other ways of correcting for multiple testing and so on. So there's lots of other things you could do, but I'll just mention the simplest one. So I wanted to start with that because that's kind of the easiest graph. It's just showing you which things are highly correlated with which other things. All right. But probably when you started to learn about graphs, you learned about something a little bit more subtle, which had to do with conditional dependence. Right? So you probably could start to draw graphs like this. So let me just say, how many people have done at least some undirected graphs before? Not everyone. Okay, so I'll start from scratch. So when I draw a graph like this, before we get into the official description, just intuitively, when you draw a graph like this, we're no longer interpreting it as a correlation graph, we're interpreting it as an undirected graphical model, which means the way to read this is that x and z are independent given y. If you understand that graph, you pretty much understand all of it. We're going to draw more complicated graphs, but that's the idea. If y blocks the path from x to z, that's to be interpreted as meaning x is independent of z given y. Let's just remind ourselves what that even means. So first of all, I'm going to write x. Actually, let me read this way. So x. Oh, viral. I mean, I know when I make a mistake, people get upset, but I didn't know what. Okay, so in this one, x is independent of y given z. So the way I write that, and the way some people write it, is this. X independent of y given z. Let's remind ourselves, what does that mean? Well, one way to think about it is the probability function for y, x and y, the joint distribution, conditional on z, factors. Right? It's the probability of x given z. So what we need to do, though, is tie these two things together. Conditional independence is something to do with probability functions. And graphs are just these pictures. And the relationship between them is in some sense intuitive. I think you get it from looking through here. But it's actually a bit more subtle than one might think. So let's go now to d. I'm going to violate my rule already. This is one observation, but I can't bear to keep writing those brackets. This is one vector with d covariance, all right? So I'm going to have a graph. This is one observation. And I want to describe the graph for this. What does that mean? The graph has vertices and edges, one vertex for each feature. And So I might have something like this, and maybe I'll call them in some cases X, Y, Z, W, whatever, just so I don't write down numbers. Here's one. Let's draw a more complicated graph. So you see, in this case, there's actually 5 features. And so there's 5 vertices, and there's, in this case, 1, 2, 3, 4, 5, 6 edges. The important thing about graphs is this: the edges do not carry information. It's absence of edges contain information. That's the way to think about a graph. And in particular, if I want to read off conditional independence statements, what I'm looking for are which things are blocked by which other things. So if I look at, let's take this set of variables, and this set of variables, and notice that any path from this set of variables to this set of variables has to go through Z. So we say that, we're going to write that as saying that Z blocks all paths between here and here, and the interpretation is that, the probabilistic interpretation is whenever we write that, we mean that this set of variables is conditionally independent of this set of variables. That is, in general, I'm going to write this to mean that all paths between A and B are blocked by the nodes in C. These could all be sets of nodes. And we interpret that to mean that XA is independent of XB and XC. So in this case, we're saying X and Y are independent of A and B, conditional on C. That's how we read off. You can read off any independent statements from a graph that way. If you learn directed graphs, what you saw is the rules for reading off independence from directed graphs are much more difficult. Rather than something called deseparation and so on. Undirected graphs are very easy to read off. You just ask, can I get from there to there? Do I have to pass through there? Think of this as just blocks the water from getting from here to here. That makes them conditionally independent. And you can see the appeal of this is I'm giving you a lot of information with the joint information. If I just gave you a density function, P, X, Y, Z, A, B, and what is a density function? It's some complicated function. And I said, look at this density function and tell me is X and Y independent of any given Z. You'd have to compute the marginal distribution of X and Y given Z, and the marginal distribution of Y given Z, and the distribution of X, Y, A, B, and Z given Z, and see if they factor, and you get back the same answer. It's a very difficult algebraic problem to check, given an arbitrary distribution whether certain things are conditionally independent of. But with the graphical representation, you can just read it off. That's the appeal of this. Is it's kind of, a very simple way to summarize the properties of the distribution. In fact, one of the subtleties is this doesn't represent a distribution. It represents a class of distributions. Because there are many distributions that have these independence relations. But before we get to that, let's do one more example just to make sure the basic definition is clear. And then we're going to formally define the so-called Markov set of distributions that are Markov to a graph. So let's do this example. Square x1, x2, x3. Again, if I had a fully connected graph, there would be no conditional independence relations. It's because there are missing edges that we can find some conditional independence relations. So give me an independence relation that you can read off from that graph. Something is independent of something given something.
X1 is conditionally independent of X4 given X2 and X1.
Right. X1 is conditionally independent of X4 if I condition on these two things, because once I've conditioned on those two things, there's no path one thing to the other. So X1 is independent of X4. I don't need that. Given, but I have to put both of them there, X2 and X3. Okay, and I think you can see there's a obvious one like this. X2 is independent of X3 given x1 and x4. And I think that's it. And by the way, if I write this, you can interpret this as what? X1, sorry, X is independent of Y given the empty set, which we just write as X independent of Y. So regular independencies can also be written. Okay, so is it clear how to read off the conditional independence relations? Any questions about that? It might be non-trivial, right? If I made a very complicated graph and said list every possible conditional independence relation, it's not obvious that you could do that easily, but at least in principle, we could do that, right? We could take any two subsets and see which things belong to paths and see which things are independent. All right. But as I said, when we write down a graph, we're really talking about a collection of distributions. So this can get a little bit confusing, and I think one way, I have a kind of non-traditional way of defining this, which is to think about listing out independent statements. So here's what I mean. Suppose I wrote down a graph. I'm going to write I of G to mean the list of independent statements you could read off that graph. So for example, in this graph, I would consist of this statement and this statement. It's just a list of statements like this. If I give you a probability distribution, and if you had infinite computing, or a lot of computing, it wouldn't take infinite computing, and you've never heard of graphs before, you could still figure out which, you could also read off a bunch of independent statements. If I tell you, here's the distribution, P of x, y, z, and I give you some complicated formula, you could start checking, well, is P of, I can compute using the rules of probability. You know how to compute the probability of x given z, right? You would get the joint distribution of x to z first by integrating on y. Then you would condition on z. Then you can say, well, I can find the probability of y given z. Then I can check and say, is that equal to y given z? Oh yes, I'll include that in my list. So again, I'm not saying this is what you're actually going to do with this, but in principle, you can take every possible conditional independence question by doing lots of integrals or sums and multiplications. You can check and get a list of independent statements. So this is the set of all independent statements that you would read off a particular graph, and this is the set of all independent statements if I gave you a particular probability method. Okay? Just think of them as lists. And now, we define the following thing. You give me a graph, let's say this one. The set of distributions which are Markov or consistent with that graph. And here comes the part that confuses people. It's the set of all probability distributions such that I of G is contained in or equal to I of P. This is called the global Markov condition. If you've never seen this before, the surprising part, that's a bit confusing, is why didn't I write E? So I'm saying that the things that are consistent with this graph have the property that if I could compute the independent statements for P and look at that list, this list should be a subset of it, or equal to it. It doesn't have to be equal, it must be contained in it. What that means is, if I read off the independent statements from the graph, I won't make any mistakes. I'll get correct independent statements. But I might miss a few. You're not guaranteed to get all of them. Sometimes when they do these graphical models, they don't mention that fact. But I'll show you a couple of examples. In fact, you might wonder, what if I require them to be equal? That's called the set of faithful distributions. It's the set of distributions P. So these are faithful. And the going to ignore because, one, it's going to cause a lot of confusion, but you should at least be aware of the difference. But I'm going to give you a little picture here, all right, that I hope will set your mind at ease. If this is P of G, so I've given you a graph, and this is the set of all distributions that are consistent with that graph. In other words, if I read off the independent statements from the graph, and you check your distribution, you go, yep, that's consistent with my distribution. And then there's the faithful ones, and so let's call the unfaithful ones to be P minus F. And the good news is that it's a small set. These are the unfaithful distributions. It's a set of measures 0 in some sense. So you can, which is why we're going to basically ignore the distinction. It turns out in certain, depending on what problems you're solving, for certain types of problems, this set of unfaithful distributions matters, even though it's a small set. For what we're doing, it's probably not going to matter. So I want to mention it just so I'm clear about what these things mean. But you should keep in mind that there could be these unfaithful distributions. What does that mean? It means this distribution is consistent with the graph, but it might have extra independence relations that aren't represented on the graph. Let me give you a trivial example so this will be clear. Suppose I have two random variables x and y with this graph. What is, so this is G. What is I of G? What is the set of independent statements you can read off that graph? Empty set. What is the set of distributions consistent with that graph? All distributions can do it this way, right? So P is all distributions. All distributions. That is all. However, the set of all distributions, here's the set of all distributions, contains within it the set of distributions, we'll draw it like this, that happen to factorize. A distribution that makes x and y independent, right? So a distribution that factorizes is actually part of this. Putting the thing here doesn't mean x and y are dependent. It just means you can't conclude that they're independent. This is why it's a little bit subtle. I think either I said something backwards there or correctly, I'm not sure, but the point is that this is just saying I can't read off any independent statements. This distribution is Markov to this. It just happens to have an extra independent statement that's not represented by this graph. Okay, so maybe if that's confusing you, forget about it for now. Because I do like to mention it just because part of defining these is good. And in a few minutes we're going to see there's that's a trivial example in some sense. But there are non-trivial examples. For example, in a few minutes I'm going to relate undirected and directed graphs for those of you using directed graphs. And we immediately are going to come across unfaithful distributions. But don't worry too much about them. It's a small technical point. The important thing to remember, by the way, practically speaking, is that when we fit these things in data, and you get a graph, you read off the independent statements, you can't rule out the fact that the distribution you might have a few extra ones that aren't represented by the graph. That's all. Now, there's another condition that's sometimes called the pairwise Markov condition. A graph satisfies, or a distribution satisfies the pairwise Markov condition with respect to a graph, which means that if there's no edge between two nodes, say I and j, we're going to interpret it differently. We're going to interpret that to mean that xi is independent of xj, given all the rest of the variables. This is a slightly different way of reading a graph. This is saying, let's draw a graph. Before, I talked about reading off conditional dependent statements by talking about something is independent of something when it's separated by something. Now I'm saying just look at two edges only. What if I interpret this to mean this is independent of this given everything else? Suppose I think of that as how to interpret the graph. Does that give me the same interpretation? Is the pairwise Markov condition the same as the global Markov condition? That is, if I wrote down the set of all distributions which satisfy the pairwise Markov condition on this graph, and if I wrote down the set of distributions which satisfy the Markov condition, but I get the same set of distributions. Yes. Subject to a very minor regularity condition, which is that the distribution is positive, which we will assume throughout, otherwise all kinds of weird degeneracies can occur. So assuming we're dealing with either a positive density or positive probability mass function, which we will assume, the pairwise Markov condition and the global condition are equivalent. You can read the graph either way and you'll get the same answer. When we do log linear models, it'll be much more convenient to use the pairwise property, but sometimes one is more convenient than the other. So this is global is equal to pairwise. Let me make sure I'm not going too fast. Is that clear? Any questions? Okay, I'm just giving you rules for how to read off independent statements from graphs. I've now given you kind of two different ways to read off independent statements, but subject to a minor regularity condition, which we will assume they're equivalent. In fact, there's a third way to read off a graph, which subject to the same condition is also equivalent. And the reason for writing all these different conditions down again is because depending on the context, one might be more convenient to use. This is the clique representation. So what's a clique in a graph? A clique is a fully connected subset. Okay, so clique is a fully connected subset. So let me draw X, Y, Z, W. Is X, Y a clique? Yes, because if I just think of two variables X, Y, the clique graph is just an arrow between it, which we do. Is XW a clique? No, just okay, a maximal clique is a clique which is maximal, which means you can't add another edge and maintain the clique property. It's a clique, but no longer a clique if you add another edge. Sorry, another node, thank you. Thank you very much. Node, thank you. So here is XY a maximal clique. Would it maintain fully connectedness if I add some other node? It's not maximal, right? Because I could add in Z. And it stays fully connected. But is XYZ a fully connected? Well, again, is it maximal? Yes, because if I tried to add in anything else, I would no longer have a fully connected graph. So XYZ is a maximal clique. ZW is also a maximal clique. And again, subject to the positivity condition, we have that another characterization of the distributions that are Markov with respect to the graph is simply that I can write the probability function or the probability density function, depending on whether we're doing discrete or continuous here, as a product of positive functions over all the maximal cliques. clique potentials. They're just any non-negative function. They're not probability functions. They're just positive functions. And these are the maximal cliques. Okay. So for example, well, let's write out the clique representation of this says that I can write out P, X, Y, Z, W as proportional to some function of the first clique. So let's call it phi 1 of X, Y, Z times some function of the other clique, which is phi 2, Z. That's called the Clifford-Hammersley theorem. It's one of those theorems, I think it was never actually written down anywhere at first. It was proved, I think Julian Bisag was the first one to actually write it down, if I remember correctly, and he attributed it to Clifford and Hammersley, if I remember my history correctly. So it's one of these folk theorems. It's in the notes. So this is kind of intuitive, right? It's saying some function of these things times some function of these things. This is how I can represent something that's consistent with the graph. And so this is kind of a nice thing about undirected graphs, is that we have these different ways of thinking about it. One way is in terms of the global markup property. A is independent of B given C, given C separates it in the graph. It's like a visual criteria. Or I can use the pairwise property. Xi and Xj are independent of everything else. There's no edge between I and J. Or I can use the clique representation. I mean, the probability function can be written as some product of functions, one for each element of the clique. In fact, you could also include non-maximal cliques in here if you wanted to as well, turns out. But you don't need, that would be a minimal error. Okay, I've gone through this pretty fast. Any questions? The hard question that we're eventually going to address in this class is, given a bunch of data from some distribution, how do I find the graph that describes that distribution? That's the statistical machine learning problem. Right now, we're still doing it at the, the population level, where we're not trying to estimate. Now, one question that always comes up is, what's the difference between directed graphs and undirected graphs? So I want to say a few words about it. If you've taken directed graphs, then this will be meaningful to you. If you've never taken directed graphs, you can ignore the next 3 minutes, okay? It's not critical for everything else we do. But they're kind of like, the way I like to think about it is, directed graphs and undirected graphs are both languages for representing probabilities and their independence relations. It's kind of like French and Italian. They're two languages. There's some things that you can express in French that you just can never express in Italian, and vice versa. Okay? And there's some commonalities. And it's the same with directed and undirected graphs. Directed graphs are very good when you want to represent generative processes. It's like a recipe. I generate X, then I generate Y. It tells you how to actually generate the variables. That's one of the nice things about directed graphs. They have the danger that you're going to interpret those arrows as causal, which is deadly. You don't want to do that. So there's disadvantages. And it's much harder to read the independent statements off in the directed graph. The undirected graphs don't have that generative property, but it's very easy to, I think, to understand what they mean. And they really are different in the sense that there are things you can represent in one that you can't represent in the other. Here's the standard examples are the following two examples. So again, if you haven't seen directed graphs, you'll just have to trust me on this. Here's a directed graph. So for those of you who haven't seen directed graphs, let me just tell you, the way you interpret directed graphs is just that this means that the probability function factorizes according to the arrows. So it's P of X, P of Y, and then P of Z given his parents. But there's some weird rules for reading off the independent statements here. Let me ask the directed graph people here, is X independent of Y in this graph?
Yes.
Yes. So that might be surprising if you've never seen directed graphs, but it's true. Is x independent of y given z? No. So again, that's surprising if you don't know graphs. The reason is, this thing's called a collider. Two things collide here. The rules of colliders are when you condition on a collider, it opens up a path. But don't worry about it. But my point is, there's no good undirected graph that characterizes the same information. In fact, the only undirected graph I could use would be, let's convince ourselves of that, because if I tried to remove any graph, I would now imply a conditional independence statement. There aren't any over there. So the only way, you can always represent things by using a complete graph, because that represents a set of all distributions. So a distribution which was perfectly consistent with these relations, if I represented an undirected graph line, I have to use a directed graph. A complete graph. What does that mean? That means it would be unfaithful. It's a correct description. It doesn't contain any false conditional independence statements. But this particular distribution that I just wrote down would have the property that there are extra conditional independence assumptions not represented by the undirected graph. Kind of a solid point. And it works in the other direction too. The other famous example, this is well known, the one we did before. We saw that A and D are independent given B and C, and C and D are given independent given A and D. And try as you might, you can play around with it, try to find a directed graph which captures exactly those conditional independence statements. You can't. So you would have to use the best way to do it would be to just arbitrarily order the variables and then make a complete directed graph. And again, that means that that distribution, which is well represented by the undirected graph, would be unfaithful to the undirected, to the directed graph. Okay. It doesn't mean there's anything wrong going on. It's just, again, it's like, again, I like the language analogy. Some types of distributions have their conditional independencies well represented in one land and not so much in the other land. There's no mistakes. It's just that your distribution might have extra independent states not represented on the graph. But we're going to be focusing on only undirected graphs. Mainly because, it's going to take a lecture or two to do undirected graphs, and we've already done, as I understand it, directed graphs, and it would take a lot longer to cover that too, so I think not the use of time to go through detail. For the real aficionados, you should know that there's people out there who have mixed graphs and chain graphs and all kinds of different weird graphs that go way beyond directed and undirected, but they get really arcane and very, very difficult to interpret. So for our purposes, regular undirected graphs. So fine, we've got this graph language. But what we're kind of interested in, and this has become very popular in bioinformatics, I give you some data, I have a distribution. That distribution satisfies, presumably, or at least approximately might satisfy a bunch of independence relations. Can I find the graph that represents those? And if nothing else, again, it's an exploratory tool, right? It's a way to look at the data. If I have 5,000 genes, it might be kind of hard to look at what's going on. But if I can find a nice, fairly simple graph that expresses the relationships, you might be able to look at it and understand better what's going on. There's the danger, by the way, though, of post-interpretation. Look, those genes are all connected. I think that's the pathway for the iron homeostasis, blah, blah, blah. So you have to be careful, of course, of over-interpreting things after the fact. Nonetheless, these can be a very useful visualization tool. But how are we going to do this? How do we fit a graph? If I give you some data, how do I estimate the graph? And this is, of course, a very big topic, so I really want to focus on two special cases, which are when all the data are discrete and when all the data are continuous. There's obviously lots of in-between cases, but I think those are the two cases that are good to focus on. So we're going to start with the discrete case. And we're going to use in particular a set of tools called log linear models. a way to estimate the distribution and recover its graph. Now, discrete distributions are ultimately, there's really only one discrete distribution in some sense. If we stick to finite range of variables, it's basically a big multinomial. Every discrete distribution with finite linear values is somehow a multinomial. But there are different ways of representing multinomials, and a log linear model is a very helpful way to represent a multinomial distribution that's going to make it easy to interpret the model and to estimate the parameters and so on. So let me explain. Let's suppose, again, I have this x. This is one random variable again. So I'm measuring on each person d things. D is the dimension. There's going to be a graph coming up eventually with d nodes. Now actually I'm going to have n of these. So I'm going to have this measured for every person in the room here. And I'm going to try to estimate the graph. I want to stick to the discrete case. And to make things simple, to avoid a lot of technical stuff, if we're going to do discrete, let's just do binary. It's not so hard to go beyond binary once we understand the binary case. But the notation is much easier in the binary case. So I'm going to assume that not only are they discrete, but each of these just takes value 0. Okay, so for every person in the room, I now have a string of 0s and 1s, which you can think of as, just to simplify matters, do you have this gene, yes or no? Do you have this gene, yes or no? Just think of that. Okay? And there's many different ways I can represent these data. When I have n data points, I could represent them as in an X matrix. So I could do x1, x2, xn, and put them in a matrix, which would be n times d. That's the full data matrix. So every person, again, is a row with a string of 0s and 1s. There's another way you can represent the data, which is very useful when you go to use R or MATLAB, which is in terms of counts. Because, for example, suppose we had 3 variables, x1, x2, x3. If I had 1,000 people, this matrix is going to have 1,000 rows. But you can see there's really only 8 possible configurations, right? Everybody is either a type 000 or a type 001. And so you could represent this as a much more parsimonious representation. And now you would have the counts. So there might be 5 people like this, 6 people like that, 7, 22, and so on. So this is the raw data representation. This is the count representation. Right? Hope everybody agrees it's the same information. And lastly, probably the most common thing is to then go one step further and represent this as tables. So I could now take these data, and this could be x1, x2, 0, 1, 0, 1, x1, x2, 0, 1, 0, 1, and this is x3, 0, 1. And we could just take these 8 counts and put them in here. So it would be 5, 6, 7, 22, blah, blah, blah. Everybody with me? This is the table representation. However, notice the following observation. How many parameters are in this model? How many things do I actually have? There's 8 parameters, right? It's a multi. This is actually a multinomial. 7, really. This is a multinomial with 2 to the d category. So in general, there are 2 to the d things. There's type 000 people. Here, I'll get 5 of them. There's type 001 two-player system. And so there's 8 possible categories. It's really just a multinomial with 8 categories. So there's 7 parameters, 8, but of course they have to add up to 1, so there's 7 parameters. That's the multinomial representation of these data, but it's not obvious if I gave you the multinomial. So if I said those counts are multinomial, and I have n of them, and there's a probability vector, P1 to P8. Suppose I even, you can obviously estimate P1 to P8 by the proportions here, right? The MLE is trivial. But even if I told you the true proportions, now I start asking you questions like, is x1 independent of x2? Is x3 independent of x2 given x1? It's very, very difficult to figure that out from multinomial representation. So the purpose of the log linear representation is to re-parameterize the multinomial, and it is just a re-parameterization, but in a way where the parameters can immediately be interpreted in terms of conditional dependencies and in terms of graphs. By the way, the extension beyond binary, I hope you see now, is right, trivial. Instead of having 2 entries in this table, I might have 5 this way, 3 this way, and so on. So I think you believe me that any discrete distribution can be done similarly, but we'll just keep doing binary computations. All right, so technically, let me write down the technical definition of a log linear model. So we're going to have, again, a vector, x1 to xd. Everything is binary. And there's a probability. So let's think about what that is. That's a probability function. The log probability function, what is the probability function? That's the probability that x1 takes value little x1 down to xd takes value little xd. Where here, the probability function takes a vector and returns a probability. So going back to our example, the probability function might look like this. P0, 0, 0 might be 1, 1. P0, 0, 1 might be 3, and so on. Think of it again. These are the multinomial probabilities. There's 8 of them here. This is the vector x. And given a possible configuration of the vector, out comes a number, the probability. So I'm just writing this as P of x. But this is a vector. And it's the probability that if I draw a random person and look at their configuration, 0, 0, 1, 0, 0, what's the probability of that particular configuration? And the log linear representation is the sum over all subsets A where A varies over all subsets 1 to B, including the empty set, with the following property. If an integer j is an A, and if xj is 0, then this function has to be 0. All right, so if you haven't seen that before, that's going to look very mysterious. But as soon as I write it out in parametric form, it'll be trivial. And we just have a chapstick break. Let's try out. So what do I mean by that? I think it's easiest to explain by a simple example. Let's start the simplest case, 2 variables. So, everybody in the population either is a 0, 0 guy, a 0, 1 guy, 1, 0, or 1, 1. So there's really a multinomial with 4 categories. And we could write this again as a table where x1 is 0 and 1, x2 is 0 and 1. And so the 4 multinomial probabilities these p's are really p00, p01, p10, p11. So what is this log linear representation? The log linear representation is this. Log of p of x is equal to beta 0 In other words, as the name implies, once you take the log of the probability, it looks like a linear model. But what's it got to do with that formula I wrote down? Let's see if it satisfies the condition. This condition says that if I take any integer of a set, and I set that x to be 0, this thing better be 0. So if I take j equals, let's try j equals to 1. Then what I'm saying is, whenever x1 is 0, that term better 0 out. Yes, 1 appears here, and sure enough, when I set 1 equals to 0, it zeroes out. 1 also appears here. And is that 0 out if x1 is equal to 1? Yes. So this term, by the way, this is the phi empty set term. This is the phi 1 term. This is the phi 2 term. This is the phi 1 term. And again, if you take any integer, well, in this case it's 1 or 2, and set that corresponding x to 0, you have to make sure that any phi term with that integer in it becomes 0. It's kind of a triviality here. If we were doing beyond binary, it would be a little bit more complicated, but don't worry about that. There's an implicit restriction here because these probabilities have to add up to 1. So these betas are essentially arbitrary real numbers. They don't have to be positive. There's arbitrary real numbers, but don't forget the probabilities have to add up to 1. But what have we actually done? This kind of looks trivial. And it is for a small model like this, but let's think about this. Here's the set of multinomial probabilities. So what does that mean? It means the vectors of the form p equal to p00, p10. These are the multinomial vectors subject to the fact that they're non-negative and add up to 1. What I've now done is I've created a new representation called the log linear representation. But here's the thing. There's a one-to-one relation between these. If I tell you these 4 p's, you can compute the betas. Conversely, if I tell you the betas, you can compute the p's. Let's actually compute them. And then you might wonder, well, then what's the point? Well, the point is going to be that the betas are very interpretable. So when you actually fit this in R or MATLAB, it's going to give you the beta hats instead of the p hats. And it's the beta hats that allow you to get the graph. Let's just look at this. If I look at, let's look at p00. That's the probability that x1 is 0 and x2 is 0. Let's look at the log of that. Well, according to this formula, all I do is evaluate it. Remember, this x here is x1, x2. I just set x1 and x2 equals to 0. That wipes everything out. So that tells me this is beta 0. And log of p01, if I set x1 equals to 0 and x2 equals to 1 in that formula, I believe I get beta 0 equals to beta 2. And similarly, this is beta 0 plus beta 1. And finally, log of p11 is beta 0 plus beta 1 plus beta 2. Right? Is that really cool? Of course, I have 4 equations and 4 unknowns, so I can solve backwards. And I'll just tell you what you get. You get that beta 0 is log the subscripts here because we're getting tired of writing the brackets. Beta 2. Sorry. I may have wanted to switch here. Not worried about it. You should check these. The interesting thing is this. When you solve for beta 1, 2, here's what you get. It's this times this divided by this times this, something that epidemiologists call the odds ratio. But here's an interesting fact that you can check. Ready? Beta 1, 2 is 0 if and only if x1 is independent of x2. You can just check that by algebra. It's just because of all these relationships, because of beta 1 and beta 2 and beta 2. You can check that. Now we've learned our first non-trivial fact about log linear models, which is simply that it's true I could represent this table or these data as a multinomial. But even if I give you a multinomial and I give you the 4 p hats, is x1 independent of x2? It's not obvious, right? You have to do some algebra. You have to solve a nonlinear equation to check whether they're independent or not. But it's a one-to-one relation, and what's going to come out of the software are the beta hats. And all we have to do is check whether beta 1, 2 is 0 or not. So we do like a hypothesis test. That will tell us whether x1 and x2 are independent. That's the advantage of doing a log linear model. Of course, when we get to more, we're doing 2 variables. When we get to more variables, it's going to get more interesting. Let's just think about, though, how you would estimate this model. If I now have n vectors for distribution P, in principle, what you could do, how would I get the log length of the betas? Let me tell you what you can do in principle. So I want to compute the likelihood function for a particular set of beta, so a particular beta vector. Fix beta. So beta is the vector How am I going to do that? Well, in principle, what I can do is a one-to-one mapping. I can find the corresponding p's. Those I have now p, 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 and now the likelihood function for a multinomial is just p to the count here, p to this count here. So I could just write this as p00 of beta, I'll call it, to the n00, which is just the number of people like this, and so on, all the way across the table. And I can now do maximum likelihood. I can get the maximum likelihood estimator. This is not the way you really do it, but let's just pretend this is how it's done. There's more efficient algorithms. But this turns out, by the way, to be a concave likelihood function, so it's an easy function to maximize. We get the MLE. What do we also get? We get the Fisher information, confidence interval, standard error, all the stuff you learned in 705. We get automatically, because this is a parametric, well-behaved statistical model with concave likelihood functions. Is it concave or convex? Log likelihood is concave. Is that concave? Yeah. And we get the standard errors, all the stuff we did in 705. And you could have done it again as a multinomial, but again, this representation is much better because you can now do a hypothesis test for independence, which would give you a graph. Admittedly, it's trivial when there's only 2 variables, but we're just starting out here. But you could look at, for example, you could test is beta 1, 2 equal to 0 versus beta 1, 2 not equal to 0, because that corresponds exactly to x1 and x2 being independent. You learned probably the test, the Wald test for doing this, where you take the MLE minus the hypothesized value And you computed a standard error, probably using Fisher information. Right? All this seems there. And then you would reject if the statistic was big. And of course, there's only two possibilities here. You're either going to end up with a graph that looks like this, or a graph that looks like this. So this is not an exciting, necessarily, example, but start. So before we do more complicated logarithm models, then, let me just pause and make sure, is everything clear about the 2x2 binary logarithm model? Any questions?
So what does convexity of the likelihood function have to do with variability in local?
Well, the convexity of the likelihood just means you can find the maximizer. But you're right, that's not certainly not required in order to do maximum likelihood. Any other questions? Okay. Well, we obviously want to consider now more complicated models. And the question is going to be, how do we interpret the log linear model? And how do we get the graph? So let's again go back to a vector. We're sticking again to the binary case, so this is a long string of zeros and ones. And the canonical way of writing out the log linear model, in this case, so keep in mind now, when I write p of x, I'm really talking about p of x1 to xd, right? It's a joint probability function. And the log linear model looks a little bit more complicated. It's going to be beta 0 plus beta j xj, j is 1 to b, plus beta jk jk plus triples and so on. Depending on how many variables. So we usually in statistics call this the main effects, the two-way interactions, the three-way interactions. Now, again, really this is a huge multinomial with 2 to the d possible parameters, 2 to the d minus 1. But there's a one-to-one mapping. You give me the multinomial and I can find the betas, and conversely. Now let's ignore estimation and suppose I actually have a true distribution at the moment. And I find the betas for you, and I write out the model. Many of those betas might be 0. And the question is, how do we interpret that? And here's the interesting thing, which is proved in the notes, which is suppose that let me write it this way. The way I wrote it in the notes is actually that's not good. Well, let's do this. X, if I have a set, this is some subset, and this might be x2 and x3. And this is some other subset. But these are independent, given the rest, if and only if the following condition holds. Whenever j is in B, and k is in C, it implies that log linear term, no, this is not right actually. Sorry. I copied this down wrong. Notes. Oh, maybe I should just do the example. Anything containing, should say, j whenever J and K appear together, it implies phi is 0. Let me explain that by, it's not very artfully written. I want you to know here. By the way, there's a bunch of stuff in the notes about how to find marginals and conditionals of graphical models. Okay, we're not going to cover that in this class. We're interested in estimating the models, not in given the model, how do I find the marginal and conditional distribution, such. That's an interesting computational question. Oh, those part of the notes we're going to skip. Okay. Here we go. Okay. If anytime, if and only all the 5 terms want to have at least one coordinate in B and one in C are 0. Let me explain what that means. This is important. This is how you read the graph off of a log linear model. And the way this is proved is by rewriting what the log linear model means and looking at how to factorize it. But let me just do an example so I'm going to read what that sentence means. Suppose that I have 3 variables now. So log of p is beta 0. It's a bit tedious, but maybe we'll write out the whole model here. So it looks like this. This is the complete model, or the saturated model, with all the possible terms. And now I'm going to put the second order terms. So 1 and 2 are here. You see it? This has to be gone. This is okay. This is okay. 1 and 2 are together. This has to be gone. That's it. This is a theorem. I'm not going to prove it. It's just algebra. But this is really important because now look, you can read off. You can see x1 and x2 are independent of everything else if I can never find a 1 and 2 together. This would be true even if there was 50 variables. As long as the pair 1, 2 never appear together, as long as those two terms 0 out, then you conclude 1 and 2 are independent of everything else, which means from the pairwise Markov property, there's no edge between them. And all you ever need to do is check pairs. So if I found 3 and 4 never appear together, that's it. There's no edge between 3 and 4. This is the. So I didn't write that quite right here. It's that J and K, yeah, that's right. Yeah, the corresponding 5 terms. I'm not talking about estimation yet again. So I'm just saying, if I took the true distribution, suppose I made up some distribution for x1, x2, x3, and in that distribution, x1, x2 were independent given everything else, which is just x3. And I found the log linear representation, it's kind of solving a bunch of equations. And I wrote it out, it would turn out that this is 0 and this is 0. It's kind of remarkable. And so we've taken this kind of very difficult question, which is conditional independence. It's not an easy thing to write down probabilistically, but it now just corresponds to checking whether certain beta terms are 0. What we're going to end up doing, of course, is, again, when we get data, is we're going to get the MLE, and we're either going to do some sort of sparse estimation or some sort of hypothesis testing or some sort of variable selection. And figure out which of these terms we can set to 0. But in this case, we've seen it's 1 and 2, so let's write down the graph. 1 and 2 are independent given 3. We now know the graph. one graph that makes x1 and x2 dependent. So it's kind of cool. We have this kind of analytic or algebraic representation of a multinomial, and then we have a graph for it. So on a test, well, you already have it. On a test, I can say, here's a model, write down the log linear model. You just write this down in 0, and you draw the terms and vice versa. It's very simple. Everybody with me? Yeah.
So if a like 3 or higher order beta is not 0, does that imply that there's a complete
good
graph of
question.
the order?
Okay, so now we get to another subtlety. Because there's other combinations of zeroing things out that AJ just kind of hinted at. What do they mean? So, for example, suppose, only the higher order term was 0, but everything else was non-zero. Let's just ask that for a second. Suppose that every term in here was non-zero except this was 0. What would the graph be? Graph.
It's going to be complete.
It's the complete graph because according to this rule, I can't say 1 and 2 never appear together. I can't say 1 and 3 never appear together, and I can't say 2 and 3 never appear together. So what does it mean to zero this out? What that means is, it's called homogeneity in this case. It's some other restriction on the multinomial, but it's a restriction that can't be expressed in terms of conditional independence relations. There are lots of restrictions you can put on models that cannot be expressed in the language of conditional independence relations. It's easy to get caught up in these graphical models and think everything about a model can be expressed in terms of the language of conditional independence. There are other things like no three-way interaction, which is called homogeneity of the probabilities, which is just some property of this multinomial, but there's no way to represent it in a graph. Is there a hypergraph representation? I don't know the answer to that. That's a good question. I do not know. That's part of the extended world of graphs that I've never stepped into. It's the part of the twilight zone graphs that I always like to think about. Okay. I'm out of time. So what I'm going to do, you can come up and get your projects. What we'll do next time, though, is I'm going to explain this a bit better. I want to explain that there's 3 layers of models. There's log linear models, there's hierarchical log linear models, and graphical log linear models. Then we'll do the normal case. So I guess we'll spend another lecture on graphical models. It's taking me a bit longer than I thought. But, again, these are all okay, but you should grab them and see what they wrote on here. I don't know if they're in any sort of order. I'm afraid not.